My name is Andreas Krennmair, and today I would like to talk to you about my experiences using Go in a real-time environment. A little bit about me. I'm developer and team lead of the ad server team at Travel Audience in Berlin, and there I've been building and scaling out the whole real-time bidding infrastructure for the last 2.5 years. I published my first Go package in November 2009, and I've used Go for proper work, as in I earn money with it for about 3 years. Garbage collected languages like Go, they don't usually have a good reputation for real-time applications. So in this presentation, I want to give you some insight how we use Go in a real-time bidding application where we programmatically buy ad impressions through automated auctions. I'll tell you a little bit about the challenges we faced over the last 2.5 years, how we managed to efficiently monitor and optimize our performance, and why I think that Go is a great choice for at least some real-time applications. So what is this real-time thing anyway? When we talk about real-time, what do we mean by it? Just ask people on the street, or ask your colleagues, or ask your parents. And the intuitive understanding is that a system of some sorts does something in an instant or as fast as possible. It's real time, it's happening right now. But computer science actually has a very specific understanding of what real-time computing means. So here are 2 definitions. A real-time system is one that must process information and produce a response within a specified time, else risk severe consequences, including failure. Another definition is any information processing activity or system which has to respond to externally generated input stimuli within a finite and specified period. So this finite and specified period is what's usually called the deadline. Real-time systems don't have to be fast per se, so the deadline can be any period of time, and that can be very specific to the respective problem domain. There are several types of real-time systems that are distinguished in literature, and the differentiation usually happens depending on the severity of the consequences in case of a failure. So first of all, we have hard real-time, where missing a deadline can mean absolutely catastrophic system failure. Think, for example, pacemakers. They need to get the timing of your heartbeat exactly right. Think anti-lock braking systems. They need to do things within a very, very short period of time. It doesn't help you if the system detects some issue with your car sliding away, and that's 20 seconds after you've crashed into something. Or internal combustion engines, then it just needs to work at an exact timing. Then there are firm real-time systems where the occasional deadline miss is tolerable, but it degrades the overall service quality, and the result is absolutely not useful. So some examples are telephony systems. If your phone just doesn't properly pick up a call, then you can't receive the call, and that's useless for actually using the phone. But it doesn't have that much of an impact because you can just redial, and it will then eventually work. Real-time bidding, which I'll be talking about, is also one of those firm real-time systems. Another example is robot assembly lines, but they can border on hard real-time depending on how things are specifically built. So it's not strict categories, it's a continuum really. And then finally, soft real-time, where the usefulness of a result degrades after the deadline, thereby degrading the overall service quality. Think, for example, computer games. When there's a lag, it's not really great because you're gonna get fragged and you lose the game. Or video streaming, it just needs to receive the data and decode it and render it 24 or 25 or 60 times a second. If that doesn't quite work out, then the video is stuttering, but you still get most of it. Or climate control systems, climate control units in rooms. It should react at an appropriate time, but it's nothing that it can do in an instance, and it's usually fine if it keeps the right temperature over the course of just a few minutes. So real-time bidding, which is what we're doing as a real-time application, it is a fully automated second price auction of individual ad impressions with a quite strict deadline of typically 100 to 120 milliseconds. That is kind of the industry standard. RTB has been an emerging trend over the last few years within online advertising. Advertisers, which are, well, the ones that want to show ads, and the publishers that have the ad space, they can automatically buy or sell individual ad impressions, usually via other platforms like so-called demand-side platforms and supply-side platforms, and they're kind of connected through ad exchanges, and there's a whole industry around all that, and can get quite complicated. The buying process, as I said, it's a fully automated second price auction. Second price auction means everyone is putting in their bid, and the one with the highest bid wins and pays the second highest price. Don't ask me about the details. The background to that is apparently there is some mathematical proof in game theory regarding Nash equilibrium, and it's kind of the optimal thing that you can do from a game theoretic point of view, and pretty much everyone really in RTB uses that. So in this whole ecosystem, my employer, which is Travel Audience, we are a DSP, a demand-side platform, specifically for the travel industry. So we work together with advertisers, we directly work together with publishers and kind of connect them, but we also employ real-time bidding to buy individual impressions for advertisers. The core concept of ours is really the ads that we show are catering specifically towards a very recent travel-related interest of a user, or the travel-related interest of a user right now. Users are usually identified by unique cookies. We synchronize them with the supply-side platforms so that we can track them. And we learn these travel-related interests of the user through travel websites that we're cooperating with, and we process them on our end. And we really only use the most recent data, and we put users into groups, but it's usually called a segment, based on their travel destinations and the type of products that they're interested in, like a flight, some last-minute travel offer, things like that. So the basic problem is we basically have this set of travel-related offers from all the advertisers, and we're trying to get the best match of these offers with each of the segments that we formed, based on the availability of offers for specific destinations or destinations nearby, because that could be interesting for a user as well, and also based on previous click performance. Like what is an ad where the user is most likely to click on, because that will most likely be the one where he might be interested in. So this whole processing, it's continuous, it's running in the background, it's pre-calculating data, and it's then consumed by our main component, the bidder. This whole bidding process, it works like that, that the SSP sends a bid request to a user that we've previously registered with them, that we've previously seen, and it contains the unique user ID, it contains a URL, contains an ad format, a user agent, device type, some very general geographic location based on geo IP, and so on. It's usually a bit specific on the SSP. With the user ID, we look up a destination or the destinations and product types that the user is interested in. Then we look up offers or display banners and that are available for these destinations. And if we've identified something that we can actually show, we calculate a bid price. This is usually based on a fixed price per ad impression or based on a predicted click performance if we are being paid, or sorry, if the advertiser is charged per clicking instead of per impression. This is actually not that interesting. It's just, the different billing models within the online advertising industry. The bid response goes back to the SSP as an HTML snippet, and it also indicates what specific size it has and what the bid price is. And we, of course, need to send that bid response on time, and only then it will go into auction. So that's this deadline that I've mentioned. And if we win, the HTML snippet that we transmitted is displayed. We are being charged the win price, which is the bid price of the second highest bid, the second price auction that I mentioned. So how did we start with that whole thing? Colleagues of mine, it was actually before I started working with travel audience, started implementing real-time bidding in about late 2013, and using Go was actually more of an experiment. The previous attempts that were done in C, and that development process was hopelessly inefficient, and it eventually failed, never got any proper results, so the decision was to try Go instead. But the Go suitability for something like real-time bidding was more or less unknown. I joined the company in March 2014. At that time, the code base was really compact, and the setup was quite simple. We were just connected to one supply-side platform, which was Google at that time. We had 2 servers that handled all the load. We received about 2,000 bid requests per second, and our data store was Memcached. We very quickly started tracking metrics like the bid request rate, the bid rate, and medium maximum duration of handling such a bid request. We actually got pretty good support from our SSP and their technical account managers, and we had a few conversations. And in one of these conversations, we actually learned, because we didn't exactly care about this specific deadline, we just tried to be as fast as possible. We were actually inadvertently penalizing ourselves. So that the reason for that is the following. Any bid response that is coming past this 100 millisecond deadline is counted towards an error. And participants that have an error rate of 15% or higher, they are just getting throttled. Do you remember the definition of firm real-time earlier? Occasional deadline misses are tolerable, but degrade the overall service quality, and the result is not useful. The deadline misses, they were tolerable because the company didn't immediately go bankrupt. The overall service quality was degraded because we actually missed out on bid requests, and you could lose most of them if you had a lot of errors. And the result was not useful at all because we didn't take part in that individual auction anyway because we submitted our bid response too late. So how do we minimize the impact of that? The solution was actually pretty straightforward. We just had to look at the specific timing. We determined that the network round-trip time from the SSP to our bidders was around 15 to 17 milliseconds. The SSP's deadline was 100 milliseconds, and we simply decided to abort our code after 75 milliseconds. Why 75 milliseconds? Because 75 milliseconds plus 17 milliseconds is quite a bit less than 100 milliseconds. So we even had some wiggle room if anything goes wrong. And after these 75 milliseconds, if we were finished finding any useful result, we will simply return, we don't want a bid at all. We were sending a no bid request. The end result was equally useful because we were not taking part in that auction. And the service degradation aspect that hit us earlier was completely averted. The solution to that was actually really simple. It's so simple, I'm almost ashamed to show it, because that was the code how it was before. Find some offers and send them back. And the change to abort the code was find offers and put them on the channel, and if after 75 milliseconds nothing has arrived, then just send an empty response, otherwise send the response that you got from the logic. It's really awfully simple, but it turned out to be super effective, and with that we could really exactly control and track our processing times. Later we refactored the whole thing. We added a cancelable context object so that we could stop any processing in the background as soon as possible as we hit our internal deadline of 75 milliseconds. So yeah, a major factor that had an impact on our overall performance was our underlying data store. We started with memcached. The data was pre-computed and was regularly loaded into it. The performance was absolutely fantastic because it's memcached. But we had one issue. We had 2 minutes out of every 30 minutes where the bidders were inoperable. We had to expunge all the data and reload it from a CSV file, and there was quite a few gigabytes, and it just took 2 minutes. We had to expunge all the data because otherwise it would have been completely inconsistent, and we would have played out the wrong offers, would have had some overspending on some campaign budgets, would have produced too high or way too low bid prices, something like that. So it wasn't a good long-term solution. We had to find something else. So it has already been, or it had already been decided before I started to eventually move to MongoDB, and there was a lot of initial enthusiasm because it seemed like a good enough solution to our problem, because our complete working set of data fit into memory. So we expected the performance to be reasonably good. We expected most reads to hit the page cache and hardly ever to actually hit the spinning disks, which would have meant quite the performance penalty, actually. Our setup was like that. We had a primary node, and from this primary node, we replicated the complete set of data to all the secondary nodes on the individual bidder servers. We introduced a local instance because that way we could just get around any network latency, which would have hit us immensely. So if you have even if you have an internal network latency of just 0.1 millisecond, you actually cannot do that many database queries within the 75 milliseconds when you have a lot of things to look for. Our queries that we were using for MongoDB, they were actually quite simple. So we essentially used it as a key value store where the value was more or less structured data. But we put the whole thing into production, and we realized we were wrong. We were very, very wrong, and we had great amount of latency everywhere. But we lacked the comprehensive metrics to really gain insight into what was actually happening. So we resorted to our tool of choice of debugging and introspection at that time, printf logging. And one pattern really emerged while we were doing that. I think I've seen it in very similar shape and form on at least 2 other slides yesterday and today. So it's this simple pattern. You just determine the current time, defer a function, and in that function you then determine the difference between that first timestamp and your current time, and that way you can really quickly collect a lot of time data, because you can put these, well, you can even put it in a single line. You can just put that everywhere and you collect quite a lot of data very quickly. Again, it's stupidly simple, that pattern, but we very quickly identified just very few problematic functions and queries, and we fixed those bottlenecks. One thing that also bit us quite hard was our logging library. So we experimented with a few logging libraries. We at one point tried to switch to this Go port of glog that you can find under this package path. And right after the switch, we noticed a highly increased amount of internal deadline misses. And switching back to what we'd used before helped a lot. And so we started digging into the library code. What was actually going on? And it was it didn't take long until we found the issue. And there was one critical code path where there was one mutex that would often get locked and unlocked. And it just caused a log contention whenever you were calling warning or error or info or fatal function. You could implement a guard, so you could use verbosity and use the v function in if blocks, but you would have to wrap every single line of logging, and that was So the lesson from that was definitely the devil is absolutely in the detail, and the most inconspicuous pieces of code coming from parties where you think, oh, they care about performance a lot, and they have probably battle tested that for years and years. Do not immediately trust third-party code unless you've really tested it. And well, we haven't done with that. And a simple mutex just in one place had an absolutely detrimental effect on our performance. The various issues that we had in our day-to-day operations of MongoDB, I came up with this phrase for that: spontaneous self-combustion, and some rather unpredictable performance, and the increasing amount of bid requests because our business was growing. We eventually decided to ditch MongoDB. We were looking around and thinking, is there a proper real-time database? It's practically impossible to find a database that gives you a real-time guarantee. So we went for the next best thing, something that is as fast and as low latency as possible. And so what we then tried, and where we put all our data that is consumed by our bidders, is through Redis. With Redis, we expected not exactly, but vaguely the same behavior and the same performance characteristics, not unlike memcached. Plus, we had simple replication, we had some persistence, so things just seemed a bit better. The migration took a while because some of the software related to a lot of offline processing depended on very specific MongoDB specific features. It was a bit hard to adapt, but we eventually made it. One thing that we had thought about beforehand was we had to split up the data into separate Redis instances, because well, you are very quickly running into some how should I say? When you have a single-threaded thing, it very quickly slows down if you just put too much on it, and you just need to have some way of sharding your data. So after all that switch was done, again, we had a very similar setup of where we had a primary instance or several primary instances that were all replicated to secondary nodes directly on the bidder machines. When that was all done, and the bidder only consumed data from Redis, we had a very sudden and very drastic drop in deadline misses on our system, and I'll show you a screenshot of that. So, because it's not entirely visible in that screenshot here on the y-axis, you have the deadline misses per second. The different colors are the different instances, and here's like the 1 p.m. and here's the 2 p.m. line. And so you see it dropping from between 50 and about 125 down to a lot less than 50. It's probably around the 10, 15 deadline misses per second range. And that was pretty good. One thing or another thing where we haven't run into that issue yet, but that can eventually get an issue. We have the single-threaded problem, so you need to shard or kind of divide out your data into several instances. And that can only work as long as you can put all your data into the local memory. If you are going over that, if your working set is way larger than that, you need to find another solution, need to move it to external machines, and that means network latency. And that's the point where you then need to start looking into doing as few database queries as possible. So, as I've mentioned earlier, we had our self-built system to track a few metrics, and we managed about 1 year with a homegrown solution. We had a little dashboard as well. We tried experimenting with XVAR to get data out, but we weren't really happy with it. So when Prometheus was announced, we tried out that, and what can I say, that was our big paradigm shift. We were initially absolutely impressed by both its simplicity and by its flexibility. We almost immediately set up a proper production instance. We initially used Promdash. We later switched to Grafana. And it really only took us a few days to get properly started. That whole setup very quickly replaced our handmade dashboard. It provided us with much better insight. And one thing was we could migrate a lot of logging from our normal unstructured logs into Prometheus metrics. It just happened to be the one tool that we missed, where we could just record events that were happening in a reasonable amount within our bidders, and we would have such a great visibility on everything. And our approach now is we just set up metrics for everything that we're building anew, and we're setting up metrics for what's going on internally, because it's absolutely cheap to keep those with Prometheus, and they are very quick to create. So once you set up, it takes like a few seconds to add a new metric, and you deploy that to your system, and you then have that metric available, and it's an incredibly simple and powerful tool. There's only one exception. That's another thing that hit us once. The Prometheus summary type of metric, don't use it in a tight inner loop of a handler with really high parallelism. There's actually a bit more going on in a summary metric, and it caused some log contentions. We then, looked into the source, looked into the documentation. It's actually documented. We should have read the documentation. To give you a bit of an overview what metrics we're tracking, a very incomplete list just to give you some insight. We track all the incoming bid requests, including what instance are they coming from, what country is the user from, what's his device type, what's the SSP, is that bid request coming from any direct deal. So a direct deal is something where an advertiser and a publisher can negotiate a certain price for which they get basically a preferred deal to buy an impression. Then all outgoing bid responses, that includes the campaign type of what we played out, the invoicing type, again, country, device type, if a direct deal ID was chosen, so if we chose to take part in such a deal and buy an impression for a specific preferred price. Then, of course, the duration of individual bids, the amount of deadline misses per server, the amount of recovered panic calls, cache hits, cache misses in internal cache objects, or as another example, bid requests with unsupported ad format sizes. At some point, you determine that bid request is for an ad format that I don't actually support. Just add one line, log it, and you have it in Prometheus, and then you just type in a quick line in the console, and then you find the list of the most common ad formats that where you're receiving requests and that you don't support yet, and then you can tell your product manager, we need to have these new formats implemented, and we can gain this much more potential of ads that we can show. So it's a tool that adds a lot of business value. But sometimes just tracking metrics for your overall performance is not enough. If you have some weird slowness or some sudden changes in behavior, you need some more detailed profiling data. The natural choice for that, and there's already been an absolutely great presentation about it today, is Go's built-in profiling capability. Initially, we used the RealTime pprof package from Go standard library. We very quickly switched to net HTTP pprof. It's incredibly simple to use. Just import the package, start an HTTP server, and you can remotely profile your software. You have one simple command line tool that collects your CPU profiling data, and it can provide you with a textual representation or a visual representation, and that makes it very easy to pinpoint where is something going wrong at the moment. And there are different HTTP endpoints for profiling data, so it's not just the CPU profiling. You can profile your heap allocations. You can profile what code, what Go routines are blocking. For the blocking, you need to set your block profile rate, and that's the only additional thing. I really cannot overstate this for introspection. Having such a powerful remote profiling tool that just comes as a standard tool in the standard library as part of the command line tools, and that can be integrated with just a few lines of code. It probably has been the most valuable feature of Go for us. In the past, it has helped us to directly introspect our live system and to analyze runtime performance while we were experiencing any performance issues on our live system. We didn't have to do any special preparations. There were no debug builds, no profiling builds, nothing like that necessary. It was especially valuable for performance issues that were just unreproducible on a test system. And practically, we had no noticeable performance penalty even under a very high load. Another tool that I would quickly like to point out is XNet Trace. Like net HTTP pprof, it's rather easy to use. You just import it, start an HTTP server, and you then create trace objects to which you can attach log information where you just put in request-specific things. You get a web interface like that for free, where you can have a look at what you've been logging on a per request granularity. And you even get some nice latency diagrams. It's all for free. It's basically the fancy version of the printf logging that I showed you earlier. It's absolutely fantastic. You don't actually see that many people writing about it, mentioning it, but it's another really, really valuable tool. And last but not least, I'd also like to talk about garbage collection. We still are under real-time constraints, and yeah, it's a complicated topic. So in real-time systems, garbage collection is usually the main point why certain programming languages aren't even considered in the first place. Because garbage collection, it adds latency to the system. It's usually some stop-the-world approach. And garbage collection, it has a kind of a stigma, I would say. Even though there have been efforts to build real-time garbage collection algorithms. One of them, I think it was one of the first serious attempts, was Metronome by IBM, which is the original paper is from, I think, 2003. They said people want to use, at that time it was Java, people want to use Java for real-time things, and so everyone in that community was looking at just manual memory management. And they instead decided to still go with some garbage collection algorithm that just followed a completely different approach. So our practical experience with Go and real-time systems, as I said, it was an undiscovered country. It started with Go 1.2. Go 1.2, it had if we remember correctly, concurrent mark and sweep garbage collector implementation, which was mostly precise. Then got fully precise with Go 1.3. More was done about the whole concurrency aspect. I think it was a concurrent sweep phase that was introduced, and the promise then was to vastly reduce garbage collection times. For our application, the Go 1.3 behavior was practically good enough, but from a real-time perspective, it was nothing that you could exactly rely on. So when we're talking about real-time garbage collection, what are the required capabilities for a garbage collector to be considered real-time? It needs to guarantee a certain amount of mutator utilization in a given time window. So the mutator is the program that mutates the graph of objects. It needs to account precisely for all mutator interruptions, and it needs to ensure that the space bounds are not exceeded. The last thing is important because, well, if you had unbounded space and didn't care for that, well, garbage collection under these circumstances is trivial because you never clean up anything. So that's one thing that made the Go 1.5 garbage collection so interesting when it was first announced, because a stop the world deadline goal was introduced, and the goal was to have at least 40 millisecond mutator utilization per 50 millisecond time window. So with that information, let's just check the garbage collector goals with these requirements for a real-time garbage collector. It guarantees a certain amount of mutator utilization in a given time window. It precisely accounts for all mutator interruptions because there are no interruptions longer than 10 milliseconds. And it ensures that space bounds are not exceeded. The last one is not quite obvious what that means. So the program, it may exceed the amount of overall memory that we as programmers wanted to take up, but not the amount of memory that it is estimated to possibly take up. This whole problem is discussed in detail in the Go 1.5 concurrent garbage collector pacing design document. It discusses how to minimize both heap growth over and undershoot, and in particular an overshoot would mean that the program consumed more memory than it was actually desired. And so these design considerations exactly take care of ensuring that space bounds are not exceeded. Overshooting was still a bit of a concern for Go 1.5 under quite extreme conditions, but these concerns were addressed by the work that went into Go 1.6 and the Go 1.7 garbage collector, and it's really improved a lot since then. But the truth is, I'm actually not an expert on garbage collection. I keep myself generally informed about what's going on in the Go development, but that's about it. So instead, I quickly want to mention a few practical side of these things. So thanks to our fancy metrics and monitoring system, we can keep track of the garbage collection performance. And so since Go 1.5, we had practically no deadline misses. Since Go 1.6, and even more so since Go 1.7, we practically just see sub-millisecond pause times from the garbage collector for the vast majority of garbage collector pauses. And it's well below this 10 millisecond maximum. It's not a strict guarantee, I want to point that out, but when you're looking at here I've got the median pause time, and here I've got the absolute maximum pause time. That's over a 24-hour period, and the highest line up here. That's, I think, 15 milliseconds, or is it 12 milliseconds? I'm not 100%, no, 12 milliseconds. So it's hitting 12 milliseconds once, and 11, a bit over 11 milliseconds twice over the course of 24 hours. So that seems pretty good for me. So with all these techniques that are briefly discussed, how large have we actually grown our system? So we're now at 20,000 bit requests per second. We have 9 servers. We have integration with 7 SSPs, and in practice we see less than 10 deadline misses per second. The practical maximum to which we were able to push a machine was 6,500 bit requests per second. And even at that point, we only saw about 1 deadline miss per instance per second. When we pushed it further, deadline misses went up, but there was a simple overload situation. The Redis instances and the bidder were just fighting for CPU, and it's obviously, well, you just need more machines to cover that. But it was a great test to see that the latency remains reliably low up to the point where you just get to maximum CPU saturation. And I think that's pretty awesome. That's a really good quality that you can get out of the system. So to recap our experience, that I can really recommend to everyone who's working on a similar domain. Understand what real-time computing really means for your problem domain. Track all your metrics. It's incredibly valuable. It's cheap to implement, especially with something like Prometheus. Know the performance characteristics of your data store. Introspect and profile your system, even the live system. Use pprof, use xnet trace. It doesn't add a significant performance penalty, and gives you a very immediate feedback. And last but not least, know your garbage collector's capabilities, limitations. Yeah, that's it. If you want to further deep dive into any of these subjects, I compiled a quick reading list with some interesting material. And if you have some experience by yourself with Go under real-time conditions, I would really like to hear your stories. Also, we're hiring Go developers, so if you want to work on edtech stuff in Berlin, don't hesitate to approach me after the talk. And I would also like to give a special thanks to Bill Kennedy, because he was the one who encouraged me to produce the presentation and submit it here to this conference. And he basically enabled me to even sit down and well, produce all that. So thanks very much for that. With that said, thanks for attending, and thank you very much for your time.